Hello and welcome to Global Climate Change. This week we're going to be talking about a couple interesting things. We're going to be looking at a couple graphs. We're also going to be looking at proxy data and what that means and what it is. We're also going to be looking at the history of global climate change, as well as when the hottest years were. We're also going to look at Arctic sea ice decline and snow decline. So let's get started. The first thing I have here is a couple graphs for you to look at, and we put them side by side so you can compare them. On the y-axis, we have the CO2 concentration on the top graph here, and on the bottom graph, we have the temperature change. Now, the x-axis is the same for both graphs. These are going to be years before present. On the right-hand side, this is going to be right now, and then on the left-hand side, this is going to be 400,000 years ago. So this would be way back in history, and this is going to be right now. Okay, so the first thing that you might notice when you're looking at them is how similar they really are. These peaks here are almost identical on each graph. Kind of interesting, huh? And if you look the bottoms here, the lows are almost identical as well. I mean, look at these. It's very shocking. With this much data, this can give us enough of confidence to understand that the correlation between CO2 and temperature are going to be tied together. This is something that we all understand and we do all know. So moving on, we do have a history of global warming. This is something that people started noticing as early as 1938. This gentleman, his name was Callendar. He was the first to note warming and the trends associated with it. Now, he found warming of about 0.36 degrees Fahrenheit or 0.2 degrees Celsius from 1890 to 1935. He was concerned about what emissions now that we were putting CO2 into the atmosphere, how that was affecting things. So he first proposed that rising CO2 levels were mostly responsible. Now, after that, a guy named Keeling, he was famous for his measurements of CO2 concentrations over Mauna Loa. This is a big mountain in Hawaii. It does take measurements of CO2. That one, since it's closer to the equator, it has seasonal variabilities to it, but it definitely shows the trend over many years. This showing a net increase over the past 50 years, and it began taking measurements in 1958. Now, after that, there was a paper published, Mann et al. In 1999. They were the first to actually reconstruct the average northern hemisphere temperatures over the last 1,000 years. Okay, so we've taken measurements since about the 1900s. So how do we know what the temperature was before that? We started using proxy measurements. We'll go over that here in a minute. So the Mann et al., this paper that was published was the first one to not only use direct measurements that were available since the 1900s, but to go way further back in history, 1,000 years, and start looking at throughout time what's happened with our globe. Now, they found that there was an increase of 1.1 degree Fahrenheit from the 1900s to 1998, or 0.6 degrees Celsius. Now here's going to be that curve here. We got CO2 concentrations since about 1950. You can see here the seasonal variation in the CO2 concentration, but this line right here, this is going to show you the average throughout this time, and you can definitely see, I mean, without a doubt, it's been going up steadily since the 1950s, and this graph goes till 2010. Now, this graph is one that climatologists pretty much always point to. We know this graph. This one is the hockey stick graph. The line here in red, this is going to be the direct measurements. And the ones here in blue, this is going to be the proxy measurements. Yeah, and this is the year. So the year 2000 versus the year 1000. And you can see this is going to be the departures in temperature from 1961, 1990 average. So, negative 1 degree Celsius to 0.5. You can see that it's definitely kind of went up and down, but stayed very somewhat constant if you were just to draw a line through this and kind of take out all these little wiggles. until you hit, about 19, 30 or 40 here, and then it just skyrockets. It looks very much like a hockey stick, so they call it the hockey stick graph. But this proxy data, where are we getting it from, and how can we rely on it? If we don't know, then how can we figure this out? Well, I propose that you look at this picture. So when you're looking at this picture, can you tell me what temperature it is? Can you tell me how much rain they got the day before? Or how much rain they're getting in the next few hours? Can you tell me whether it's, what time of the day it is? Exactly what time. So we might not be able to tell exactly what the exact specific temperature is in this picture, but we can tell a few things. We can tell that it's probably cooler out. They've got hats on and jackets on and jeans. They're not wearing shorts or, short sleeve shirts. It probably was a certain amount of moisture. They're all wearing boots. You can tell it's probably in the fall because all the leaves are falling. The leaves are on the ground there. But, probably in the afternoon, it looks like the sun's probably, above them somewhere. It's cloudy out, but I couldn't tell you exactly what, time it is. It's definitely during the day. So this is the equivalent of proxy data. Proxy data, we don't need to know exactly what temperature it was 1,000 years ago or 2,000 years ago, even 100,000 years ago. We do need to know the idea. Was it warmer than the day before? Generally speaking, how, what were the trends going on throughout this time period? And so, we don't need to know exactly what temperature it is or how much rain has fallen or any one of those things specifically. Because remember, this is averaged out throughout many years. 30 years is actually the normal time period that they use. So since it's averaged out over such a long period of time, then we just need to know the trends. We don't need to know these individual little wiggles year to year. We just need to know, is it going up? Is it going down? What is it actually doing? Now, where do we get these proxy measurements from? Well, the direct measurements, like I said, have been available since the late 1800s, early 1900s. But before that, we need to look at other things to tell us what, the temperature trends were, what the CO2 trends were, the moisture trends were. Okay, one of the things we can do is look at ice core data. We can look at the coral reefs. And another thing, interestingly enough, is here actually in California and Oregon, where they have the redwoods, they can look at the tree ring width. They can tell how much CO2, how much moisture, if it was drought, how much sun, different things like that, just by these tree rings. But how do we deal with these ice core measurements? We can actually analyze air bubbles that have been trapped inside the ice. They can extract the air bubble and then be able to tell what the makeup of that air is that was inside of it. Also, when snow falls in Antarctica, it falls on a previous year's snowfall without melting. So it just kind of like a layer, and it turns into ice below it. Snow deeper than 80 meters turns into ice, like I said, from the weight of the snow above it. And by drilling down from surface of ice sheet, history of chemicals and ice can be obtained. It's kind of like when you drill down into sediments in a mountain. You can see the different sediments. When were the hottest years? We keep talking about this trend of warming and what's going on, but the hottest years, 9 out of the 10, have been in the modern meteorological record. They've been in the last 15 years. So the 5 warmest years are actually 2016, 2017, 2015, 2018, and 2014. We just keep getting warmer. Here's an interesting graph here for you. This is again showing thousands of years ago, how this being right now, this is going to be 18,000 years ago, and what the temperature change was. You can see how we had major times of warming and cooling and warming going on right here. But if you look, the temperature change was only a couple of degrees. The difference between here and here is really only about 1.5, 2 degrees. the difference between younger driest time and the time where it started kind of declining right here, this is only going to be a few degrees as well. So for us to say that our temperatures increased by 1.1 degrees Celsius is a big deal because we don't experience these temperature changes in very large amounts. We're not going to see a 15-degree difference. We've never seen that. Just a couple degrees actually matters. Argus is going to try and bark. Okay, so here's a summer Arctic sea ice decline. This is going to actually be up in the Arctic Sea, and what the sea ice is actually doing. You can see, again, here, time is, generally speaking, always going to be on this x-axis. On the y, we're going to have the extent in millions of square kilometers. You can see that, we had 8 million square kilometers of extent of Arctic sea ice in 1978. It's kind of wiggled, it's kind of changed, throughout time. We always have differences in our day-to-day, in our weather, the shorter period. But when we're looking at the longer period, we can just, put a nice little line here, a little fit, showing us the average. You can definitely see it's been declining throughout time. Here's a side-by-side shot, the end of summer of 1979 with the end of summer of 2007. You can visually completely see the difference here. The ice is going all the way over here where it's not even thinking about getting to over there. So we're definitely seeing a change in the Arctic sea ice. But not only are we seeing a change in Arctic sea ice, we're also seeing snow cover decline as well. You can see here the change in, just visually, you can see the change in snow cover. Much of it is gone. Now, when the snow is melting and the sea ice is melting, what's going to happen is the sea level is going to rise. Okay, so you can see that since 1880 to 2000 here, there's definitely going to be, what is this, about 20 centimeters of change. It's quite a bit, actually. And the two main causes are going to be melting of, like we said, the continental ice and also thermal expansion. So our sea levels are rising, our ice is declining, and so is the snow. But what is the Intergovernmental Panel on Climate Change, or the IPCC? What are they saying about global warming? They're saying that it's unequivocal. They're saying that further warming is already unavoidable due to the past human activities. We'll go over this a little bit later in class, or actually here in this lecture, how long the CO2 stays in the atmosphere after we actually put it in there. Most of the observed increase in global average temperature since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. I'm just going to remind you, anthropogenic is human-induced. That is what we're actually putting into the atmosphere. The rise in CO2 concentration means, the increase from 315 parts per million in March of 1958 to 411 in March of 2019. That's a 30% rise in 61 years. May 9th of 2013, the daily CO2 concentration reaches 400 parts per million for the first time. April 2014, the monthly concentration reaches 400 for the first time. In May of 2019, so this year, CO2 levels hit 415 parts per million for the first time in recorded history. According to climate models, the increase will continue during the 21st century. They're expecting 550 to 970 parts per million by 2100. Now, that amount depends on emission scenarios. We'll go through emission scenarios later on in class. Now, this to me is a very interesting graph. In 2006, China overtook the US as the world's largest emitter of CO2. So they put more CO2 in the atmosphere than anybody else does. It used to be the United States. But if you look at how much is emitted per person or per capita, then the US is still much higher. What that means is that we're putting out per person a lot more. We're driving around a lot more. We're using a lot more electricity. We're consuming a lot more meat. We're doing a lot of things that per person means that we're putting a lot into the atmosphere. And this, I think this is the last. Oh, nope. Okay, so the U.S. CO2 emissions is showing a recent decline, and this is as of 2015. It has been going up since 2016, though. So I don't have a recent graph for that, but I will say that this is a little bit outdated. It was declining as of 2015, but it's not declining anymore, unfortunately. But where we're going to go over next here for the next few minutes is going to be just CO2 in general. CO2 is the most important anthropogenic greenhouse gas, or GHG. I might abbreviate that. It has the highest concentration and the largest impact on our climate. Now, remember I was talking about the amount of time that CO2 stays in the atmosphere after we put it in there? The approximate atmospheric lifetime of 120 years. Okay, so current emissions right now will affect our climate 120 years in the future. That's why it's important to start cutting it down now. But where is the CO2 coming from? We have two sources. We have anthropogenic and we also have natural. So we have electric power generation, transportation, industry, commercial and residential. We have agriculture and land use, deforestation. So the fires down in South America right now in the rainforest is definitely going to affect our CO2 levels, because during the day when photosynthesis is going on, those plants actually will breathe in CO2 and breathe out oxygen. But at night it's actually the opposite. So that's why it can actually be a natural source of CO2 at the same time. And another natural source would be volcanoes. Now, here's a nice little depiction of the sources and sinks of carbon dioxide. You can see the fuel combustion is putting it in the volcanic activity, burning plants and respiration, soil decay. CO2 can evaporate too out of the oceans. The ocean actually is a large store of CO2. But we can also have it dissolve out of the air and go into the marine life, and then photosynthesis actually is going to take it out as well. But CO2 is not the only greenhouse gas. There are many other anthropogenic ones. They have an impact on our climate. We have methane, nitrous oxide, and CFCs, which are the chlorofluorocarbons. They have different concentrations, atmospheric lifetimes, and warming potentials for each one of them. They just don't have as much of an impact on climate change as carbon dioxide does. They're also well mixed. But another CO2 greenhouse gas is going to be water vapor. Water vapor is actually very variable. It's very highly variable. There's places like down in the rainforest where there's a lot of water vapor actually contained in the air, where up at the poles there isn't as much at all. So it's very highly variable. It only lasts in the atmosphere for matters of days because, obviously the water cycle, it rains out. And not directly responsible for global warming, but it can amplify its effects through feedback loops. And we'll go through feedback loops a little bit later in our semester. But it can affect it, but indirectly. And that is the end of our lecture. So I hope you guys have a good week. I really enjoyed the discussions that you guys put up last week. Keep up the good work, and I guess I'll see you next in week 2.